really, I'm trying to give an overview of what the landscape is of high performance computing without diving into too much detail about one particular subpart of the whole subject. As Terrascale says, I'm a member of the MBCS. I joined about 8 years ago after doing basically an academic career and then a career in industry. I thought I'd better get some letters after my name. And my email address, that's my work email address. Feel free, if anybody on this call, if you want to make contact with me, you'll find me on LinkedIn, and that's my email address if you want to ask me any questions or do any follow-ups after this. So that's my title slide. I nicked it off the internet as usual. It's by a system built by one of my previous employers, and that's what supercomputers look like, or particularly when they're marketing photographs, they look like that. In real life, they're probably, the computer room's got an odd chair in there and some piles of boxes. It doesn't quite look as pretty as that, but that's what it's supposed to look like. High performance computers take the form of racks and racks of servers in the modern world with flashy lights on them, and they're all connected by an interconnect, and they all, what makes supercomputing different to other computing, to kind of cloud-based computing, all those machines all work together. They try to present a single computer out of all those hundreds or thousands of servers and their respective cores. So high performance computing is all about harnessing thousands of components to make it appear as one computer. So when they run a job, they run one job or maybe a few jobs across all the systems together. And the challenge is how you make all those things work together viably. So in terms of who am I, there's a video of me obviously in the preview there, but that's what I look like in real life, or allegedly. So a bit about my biography. I've only had three phases to my career, and I know quite a lot of people on this course are probably at the beginning of their career. So I thought I'd give a little pan out of how I got from a school leaver to where I am now. So my first 15 years with the University of Manchester, I went there as an undergraduate, and I decided not to do computer science as such. I did civil engineering, 3 years, a bachelor degree in civil engineering. And I kind of quite liked the university and the atmosphere there, so I thought I'd stay on a bit longer. I also had a girlfriend at the time who was still there, and so I did a PhD in computational mechanics, and that's within the civil engineering department. So as an undergraduate, I was doing, there were some programming courses we did as civil engineers, Fortran in particular, and then what I did as a PhD was I developed software, finite element software, which I'll talk about, to model geomechanical problems, so tunnels, dams, foundations and things like that. And that's what got me into high performance computing, because to model those 3D problems you needed big computers. And I was at Manchester University, and Manchester was, still is, but certainly was in those days, a leading centre for high-end computing. And as you'll know from your first year lectures, the world's first stored program computer was developed at Manchester University, and of course it's where Alan Turing's searchlight used to be here, the Manchester Mark 1. You can look that up. So Manchester is one of the main places in the UK that's got the longest history of computing, of innovation in computing, and that's kind of why, even though I was doing a civil engineering degree, it's how I got into high-end computing. At the time, Manchester had a series of vector supercomputers, control data CDC computers, early Crays and so on. And the most interesting computer I worked on at the time then was that we had a Fujitsu computer, and that came from Japan. And that computer came in two big HGV trucks. One truck contained the computer and the cables and all the other things it needed with it, and the manuals and documentation and cabinets, and the other truck contained water, because that computer was water cooled. Back in those days, back in the 1980s, they still water cooled computers, so late 1980s, and the only water that was qualified to cool this vector supercomputer was Mount Fuji water. So I don't know how much it cost them to do. They didn't trust the water in Manchester. They had to import water from Japan to cool the supercomputer. So that's my kind of a unusual story. I was there the day it arrived, and they were taking out these big tanks of water. It was a cool system. So after that, after my PhD, I was a postdoc, and actually I was a lecturer. So for kind of 8 years, I did a whole rolling set of postdoc positions, doing some teaching, and then developing my research. And the kind of the high point of my research is what I show here. In fact, this is the cover of a book. My professor, head of department, was Professor Ian Smith, and he wrote a series, multiple editions of a book called Programming the Finite Element Method, which was a book showing how you write first in Algol and then in Fortran how you could program this thing called the finite element method. And I was lucky enough to get one of my computer models on the front cover of that book. So I'll say quickly what finite elements is. Finite elements is where you try to model something like a bridge, a dam, or even a car, and you divide it up into lots and lots of little shapes, little triangles, squares. In 3D, they turn out to be little cubes or tetrahedra. And each one has numerical values for things like temperatures and pressures and stresses on them. And you make a computer model out of thousands of these. And then because there's so many of them, you need a supercomputer to run it on. And I could have a guessing game if you could tell me what that model is, but I'll tell you if you like. That is, and Tiago hinted at it, that is one of the tunnels, in fact, the Atlas experiment at the Large Hadron Collider in CERN. I'm not sure if my pointer works. Let's see if the pointer works. Try that pointer. So this is a tunnel. In fact, the tunnel comes round like this and circles round all the way round across the Swiss border and back round again up the other side into the beam line. And then there's this large chamber where the detector is, the Atlas detector is, and these side ones are actually where the computer halls are for measuring the collisions. And the challenge was, and this was again in the early 1990s when they were starting to design the LHC, they wanted to tunnel out from the surface down to the existing tunnel, create these huge caverns, but without disturbing the ground too much, so they could carry on using the equipment. And also, these holes are absolutely massive. They're almost as a house could fit down one of these tunnels because the detector is huge, if you've seen any pictures of those. So the challenge was how to computer model those. And this was in the 1990s, and computers have got a lot faster since, a lot bigger since. And so what I was doing was kind of on the leading edge of writing computer models. I had to write my own computer models. There weren't packages out there that you could just use now like you can nowadays. And actually the visualization of that I wrote myself as well. That visualization is done in some software that I wrote myself. And my visualization software package was written in Fortran. Not that Fortran's the best language to do visualization in, but it's the language I knew best. And often in computer science, the best language for a task is actually the one you know well yourself. And just to comment on this is a stress analysis, and the red bits are the high stresses. So there's like a red ring going round there, down this tunnel thing going into the ground, where was a particular concern of this model. So that's what I did. So after doing that for kind of 8 years, I then moved within the university into the computer support department, and it was the time Manchester University gained the largest supercomputer in the UK, certainly the largest academic supercomputer. There was a similar sized one at AWE for designing nuclear weapons, and there may or may not have been bigger computers in Cheltenham, but we don't talk about that. So what does a T3 look like? It looks like one of these. This is a picture again off the internet. I don't actually know the person photographed there with the filing cabinet, with the ring file, but that was a T3E. And in those days, computers did look quite exciting. They weren't constrained to fit in 19-inch computer racks. And it was just the fancy logo on the side. If you took the covers off, it looked a bit more like a Harley Davidson with gleaming tubes, because that computer was also water-cooled, liquid-cooled, like I mentioned about the Fujitsu system. And it's interesting that from those days, we moved into an era where computers were just air-cooled with air conditioning. And now we've gone back to an era, the era going from now onwards is back in the era where we liquid cool our computers just because they're so power hungry. At the time, that computer there used 10% of the electricity bill of the whole University of Manchester. and that was largely because it was on all the time. It was on 24/7, whereas other high energy uses at the university were only on for kind of short periods of time, if you like heating and so on. So I did that for 3 years, and then in the year 2000, I actually got asked to run a 2-week summer school on Linux for high performance computing. And at the time, Linux was a toy, really. It wasn't taken seriously. We're still in the world where you had proprietary Unix operating systems, which were where the big systems were built with. But on the back of that, designing a system to run Linux for high performance computing, which means you could run supercomputers built out of generic parts. In fact, on that course we got the students to build a computer cluster using 4 servers that I'd managed to acquire that were being thrown out of one of the computer labs. So I did that for 3 years, and while I was on that course, I got actually a job offer in industry. So although I was at Manchester, I got a job offer in Bristol, and so at that point I moved to Bristol in 2001, and I've done the last 20 years now doing pre-sales for high performance computing. I moved to Bristol to work for Quadrix, and there's more later about that. And then I also worked for Clearspeed, and again I've got a couple of slides about that. Both supercomputing companies. I then worked for Bull, which are now owned by Atos. And then more recently, I've done 7 years at IBM, and I've just joined HPE. And so I guess if you have to have one slide to illustrate my 3rd phase of my career, then it's this one here. So this is I'm afraid it's a slightly grainy picture. It's from a magazine cover. This was in, I think, 2006, 2007, when, although Clearspeed were a small company, we worked with a Fujitsu, large company in Japan, to put in the world's first GPU accelerated computer. So the first computer on the top 500 list, again I'll talk about that as well, that uses supercomputers, that uses accelerators for supercomputing, was actually Clearspeed. Clearspeed are now long gone, and like Quadrix I used to work for, they're also long gone as well. They lost out to other competitors in the market, actually Nvidia and Mellanox in those particular cases. But for a time, Bristol shone as a golden light across the world because we had the biggest supercomputers came out of research work in Bristol. So when you think what a supercomputer looks like, that's kind of a typical view. And in this is kind of the golden era of supercomputing, when supercomputers could be any shape the vendors wanted. So they came up with these fanciful shapes and designs and lots of flashy LEDs, lots of red LEDs. And so that's Connection Machine 5 by Thinking Machines. The biggest connection machine out there was actually owned by the NSA. And that's they publicly talked about that some years later. So the National Security Agency, the equivalent of GCHQ in the USA, had a variety of supercomputers, and they actually had the biggest thinking machine in the world at the time. And so in those days, supercomputers looked very exciting, and they had lots and lots of flashing lights at the end. The flashing lights actually meant something in those days, but of course they look impressive, even if you don't know what they mean. So I haven't really said what high performance computing is. This is another high performance supercomputer, and it's one I was involved in. This is actually the ASCII Thunder system that was at Lawrence Livermore National Laboratory. So as I said, that the sites we've used supercomputers the most tend to be, apart from the intelligence agencies, it's the supercomputing history has largely been driven by the national laboratories that design nuclear weapons. So Lawrence Livermore and so on in the USA, that needed massive computing power to avoid doing physical tests of their weapons. Other big uses of supercomputing are obviously drug discovery, so COVID vaccines and so on are a result of supercomputing. And the other big one to note is weather forecasting. So in terms of weather modeling, climate modeling, global warming modeling, they're all done by supercomputers as well. So although in the past the development of supercomputers might have been driven by not so nice nuclear weapons industry. What's driving it now, I would say, is the importance of drug modelling for COVID and the like, and global warming modelling, which are both perhaps more worthy causes than the others. This is the computer I was involved with. It ran at about 20 teraflops, and I'll talk about what that is in a minute. And it had 4,000 cores of Itanium. Now, Itanium was the first 64-bit chip from Intel, designed to replace everything else. Itanium is now gone because Intel just weren't very good at producing them in a way that people could program them. So although Itanium kind of died out in favor of x86 64, and so nearly all supercomputers now are Intel style x86 64, which I've got a slide on in a couple of slides time. But that's what supercomputers look like: racks and racks of servers. The things at the ends are actually what I was involved with. It's the Quadrix interconnect. So all these rows of cabinets have servers. Each server has a couple of network cards in them, and they're cabled to the slightly different shaped rack at the end, which contains the network switches. And as you can see, there's lots of network switches. Well, I can tell you the network switches in the end of each row. And those systems, there's cables under the floor that connect them together. Nowadays, it's more typical to have the cables running over the top. So supercomputers now don't look as nice as they used to, because they look more industrial now with lots of cables everywhere. But in those days, people liked the systems to look clean, and so all the cables went under the floor. So I haven't really said what a supercomputer is, and high performance computing is the world of supercomputers. So a supercomputer has a difficult definition. Its best definition is it's the most powerful class of computers available at any given time. And so where we stand today are these racks and racks of Cray supercomputers, as you have there. But if you go back in time, you have classic computers like the Cray 2, which was circular and you had a seat on the outside, you could sit down on it. But really, a supercomputer is best described as a computer that's the most powerful of its era, certainly in terms of floating point performance. And so obviously things improve over time. So what was the supercomputer of its time? If you wait enough years, then your mobile phone will have more power than the fastest computer in the world had maybe 20 years ago, because things accelerate in terms of performance over time. So supercomputing, although it is the fastest class of computer of its era, the other thing that distinguishes it is what people use them for. So supercomputing, as I've mentioned, is dominated by big simulations, so car crash simulations, weather modeling, climate modeling, weapons modeling, and such like. They tend to be simulations. Most use cases are simulating what's happening in the real world. So although you could go around and crash lots of cars, it's cheaper and less dangerous to simulate them on a computer. Likewise, it's cheaper and less dangerous to simulate nuclear weapons on a supercomputer than do it for real. And then some things you actually can't do for real at all. So supercomputers are used for galaxy modeling. They're used for modeling how the universe started. They're used for modeling what happens when two black holes collide. Clearly, you can never do experiments on those. The only way you can study them is to do them in simulation. So how do you measure how powerful a computer is? It's measured for number crunching. It's particularly measured in floating point operations per second, or a flop. I know it's got a funny name, but it's called a flop. And one floating operation is one mathematical operation, like a multiplication. So if your pocket calculator does or your mobile phone multiplies two numbers together or adds a third number, that's a flop. One floating point operation. Humans take several seconds to do a floating point operation. In fact, humans might take minutes or hours to do a single floating point operation, even given a calculator or a large sheet of paper and a pencil. But computers can do these really well. So computers, even the early pocket calculators, could do many floating operations in a second. And so when you talk about floating point operations, you're not talking about ones and twos. You then start talking about thousands, millions, billions. And so you start going through all those Greek letters where you talk about kilo, mega, tera, giga, peta, exa, and so on. And the world we are now, we're just about to enter the era. This next year, we'll enter the exaflop era, where exa is 10 to the power 15, or 1,000 multiplied by itself 5 times, or a million, 1,000 million, something like that. No, but a million, a lot of, anyway, 10 to the 15, it's a lot. And so what the industry has done for a long time is it's tried to rank these systems and produce a public list of all the supercomputers in the world at any one point in time. And this is what's called a top 500 list. And the next few slides talk about some statistics on that. So that is the current top 500 list, the top 10. The top computer in the world is in Japan. It's called Fugaku, and it's based on the ARM processor. It's actually got proprietary interconnect. It's kind of unusual and it doesn't have a coprocessor as such. The next two are both built by IBM, who I used to work for, 2 different national labs in the USA. And what I would highlight about there is how many computer cores they have. These are not quad core or 12 core or 64 core. When you add up all the cores in all the servers, they are millions. So the Summit computer has 2.4 million CPU cores. And Fugaku is even more. In fact, that isn't even the largest. The system in China has got 10 million cores, and that's their own chip. The USA have tried to stop the sale of supercomputer chips to China because they don't trust them. And so, of course, what the China do, they go and design their own computer chips. So the list is defined by, comes out every 6 months. It has a number of cores, it has other statistics like how much power it consumes, and then it has the performance, both the peak, which is the theoretical figure, and the actual figure. And the actual figure is maybe 80% if you're lucky, maybe a bit less if you're unlucky, percent of the peak performance. And so the top computer in the world there runs at this figure of 442 teraflops, which is half of 442,000 teraflops, which is 442 petaflops, which is 0.4 exaflops, which is a big number. Just in comment, the final number is the power consumption. And actually the limit of building computers is, as much as anything, how much power it consumes. That consumes 29 megawatts for a single computer. Current electricity prices in the UK are about £1 per watt per year, per kilowatt per year. So you can quickly see that if your computer consumes 29 megawatts, that translates directly to £29 million worth of electricity every year. So only one of these computers, the computer itself costs you £100 million, but the power consumption per year is almost a third of that. Every year you'll spend £30 million on electricity. So you can see that these computers use a lot of power, and therefore you pretty much have to build a power station to go with them. And increasingly there's a pressure to make these more green, if you like, to run them on renewable energy. And the biggest computer in Europe is in Finland, and that works on hydroelectric power. So a bit more about the top 500. It started in 1993, and there's been a new list every 6 months. So there's 58 lists so far. Historically, the USA has been dominant, and then kind of Europe, kind of a close second, although Europe, of course, has many countries. But China has the most systems at the moment. It doesn't have number 1. It only has 1 system in the top 10, but it does have the most systems in total. Although because China's a more difficult country to know what they're doing, it's not quite clear what they're using these supercomputers for. And in some cases, these supercomputers may just be used for search engines and similar, not real supercomputing applications themselves, like weather modeling. In terms of share of the current list, I took a snapshot of the current list that came out 3 weeks ago. at the supercomputing conference in the USA. It was published. In terms of share, and again, indeed, you can do the share based on capacity, or you can do work out the share based on performance. If you do it share on a number of systems, of the 500 systems, the vendor with the most is Lenovo. So I just noticed there's a question in the chat. Well, I'm not sure I can read it properly. Yeah, sorry, you're right. Yes, it's a Cray 1, not a Cray 2 with the seat on it. Yes, thank you for that. And interesting that you work for Cray as well. That's very interesting. And as I'll come to, the legacy of Cray is actually, a lot of it's in Bristol now. Bristol is now a centre for R&D for Cray, which is now part of HP. So Lenovo has the biggest share, a Chinese company. HP has the second biggest share. Then after that is another Chinese vendor, Inspur. After that, I'll mention it is Atos. Atos is otherwise known as Bull, and they're a European supercomputing company. They're the only company of note that's European central, if you like. Lenovo being Chinese centered, HP is American centered, Inspur is also Chinese, Atos is a European. So it's where if you like, if you wanted to build a purely European supercomputer, you might approach Atos. Sugon's also Chinese, Dell EMC you've heard of, Fujitsu's Japanese, and then these other vendors. NVIDIA is used in a lot of computers, but they're not the prime vendor normally. Normally they produce some of the CPUs and things in there. So that's why Intel doesn't appear here. Although Intel make a lot of the chips on AMD, they don't make the whole computers. They make the chips that go inside a HP or Lenovo computer. And so I've already talked about this on the previous slide, so I won't go into it again. Just zoomed in a bit bigger for you to read the statistics of the top 3 computers in the world. So I should have given this as a question to all beforehand. What operating system does the top 500 run? And you can see that Windows has occurred. There have been a few Windows-based computers on the top 500, but very, very few. Windows, this is not the world of Windows, not the world of Microsoft Windows at all. It doesn't get a look in. There's no point. It's not designed for this large-scale systems. As you can see, the domination of the systems are Unix and now Linux, where Linux is just an open source version of Unix. So these systems have always been dominated by Unix operating systems, and now particularly Linux. And Linux took off around the year 2000. That's when I organized a course on Linux for supercomputing, when they were just starting to be, at the time I ran the course, I think there were 4 or 5 supercomputers in the world in top 500 that ran Linux. Not many at all. Now, I'm not sure there are any that don't run Linux. I think it's 100% now. Oh, there was, for a brief time, as an aside, actually interesting, there were a few supercomputers that ran Mac, particularly in Texas, I think, and places like that that had Mac-based supercomputers. What's interesting, if you want to think about it, is the new chip, the M1 chip from Apple, is actually a really good CPU for supercomputers. Apple are not interested in building supercomputers out of it, but it would be really, really good technically. So there is a possibility that Apple will realize this, and Mac OS, Apple may actually start having a large share in the top 500 list in the future. But at the moment, it's dominated completely by Linux, and there's no look in for other operating systems like this is a horrible picture because the colouring on it. What I put this slide in is to show, and this is from Wikipedia, which is why I can show it because it's publicly available, is all the different architectures that have been in the past. Where we stand today, 2020, the shaded blue is Intel, and then there's a lighter blue, which is AMD. They dominate the market. Almost everything is Intel or AMD. What's actually happened, this latest list, which hasn't got this chart because the list only came out a few weeks ago, is that the AMD proportion has grown. they've doubled again. They've got quite a lot bigger. But there was a time in the 10 years ago where AMD did, because AMD had the Opteron processor and similar, where they did make good inroads into Intel's dominance. Going back recently, the only other architecture of interest was power. There was a time when the power processor was a large proportion. Over 200 of the system were based on IBM's power processor, and then it shrank and shrank when the Intel world took over. And so during most of the 2000 era, it was a power balance between power and x86, a little bit of x86 32 at the top as well. But really, IBM have stopped competing in this marketplace, and although the number 2 and number 3 in the world are power based, there aren't many others in the top 500 list that are IBM CPUs, IBM power, dominant x86. But if you go back early on in the chart, look at the range of colors we had there. There were just loads of different architectures. There's this burst of the dark blue when Itanium had its time in the early years 2000s, and loads of systems. People thought at the time that Itanium would take over the list, but it didn't. It collapsed again. And then there was a time when PA RISC, which was HP's processor, had big dominance at that time. Again, that faded away as well. And then the other one I'd note is the only one I actually noticed, the purple. The purple with the going up stripes was the Alpha server, and I've got a whole slide about that I'm going to talk on next, about where Alpha came from. It dominated the market. It was in the Cray computers, the HP computers, the compact ones, and so on. But say there was a time when there was a large landscape of different manufacturers. Now they're all gone pretty much, and now it's just it's not as exciting, if you like, because nearly everything is x86. So this is the build-up chart of what the things have been like since it started 1993 to the current day. The vertical axis is logarithmic, and it's that thing I talked about, flops, and rather than write in flops or kiloflops or megaflops, it's gigaflops. So that's 1 billion floating point operations. So the starting point there, beginning of the list, is 10 to the 0, which is 1 gigaflop. Sorry, 10 to the 10 there, which is 1 gigaflop. So that's 1. So that is the entry point where you had to have a gigaflop performance to get on the list at all. There are 3 lines on the curve. The red is the core one. That's the number 1 system, the fastest computer in the world. And obviously, there's a point here where a system went in, actually the Earth simulator in Japan, that was so good, it pushed the curve up so much, it's 10 times better than its previous system, that it stayed in position for many years. It stayed there for 1, 2, 3, 4, 5 editions of the top 500 list. And again, there's an example up here where a system lasted many years. Otherwise, the systems tend to, each new list has a new system at the top. The dominance at the end now is I think it's the Fugaku system, which has lasted a while. But also on the graph, we've got the entry point. That's where you have to be to get on the list at all, the yellow line. How good a computer do you have to be on the list? And that's interesting because the system that made you number 1 then, by the time you reach 2005, you wouldn't even make the list. So supercomputing grows, expands rapidly. And just because you've got the best technology in the world, eventually that system won't be good enough. That multi-million pound system that got you number 1 place eventually won't be good enough to get on the list at all, because it shows how much the industry is growing. And the blue line for comparison is the total sum of all the systems. That's the total compute power of the top 500 computers. So I'll build this chart up. The first system came in at only about 0.1 of a teraflop, and so really the Terrascale era started in 1998. That's a system called ASCII Red. And actually, it was an Intel processor. It was actually a desktop processor. It was a modification of the which chip, a Pentium processor basically. It was a Pentium Pro basically, because they were cheap to produce. So they built a supercomputer after the Pentium Pros. And that's what it looked like. And so that began in 1998. We kind of got into the Terrascale era of supercomputing. And that lasted a while. That lasted until 2008, when we got into the petascale era of supercomputing, systems capable of, you can read backwards off the curve here, 10 to the 6, a million gigaflops. That's a million times a billion floating point operations a second. And that brought into the petascale era. And you can see that that era lasted 10 years. Just about 10 years, slightly over 11 years. And that system at Roadrunner is very interesting. It was built by IBM, but what was interesting about it is it contained basically the PlayStation 2 inside it. It contained, as a co-processor, it contained these PlayStation 2 chips, I think it was. And then if you draw the line, this is the boundary we're heading for. This is the exascale era on the far right. This is the point where the red line will cross this 10 to the 9 point, and I'll draw that on the curve. Oh, I should have had a build out for that. There was an arrow on the curve up there to show where we are today. That's 10 to the 9 gigaflops, and that is what we call the exascale era. And we thought the first system that was exascale would come out and be publicly known about 3 weeks ago, but it didn't. The US system has yet to be finished, and Chinese systems, they decided not to publish. So where we are in supercomputing is exciting because we're just about to hit the exascale era, the era of the exaflop, 10 to the 15 floating point operations a second. And I was noting the fact that system on a certain point on the list eventually will be obsoleted only a few years later. So just briefly, what is a HPC system? It's a whole bunch of servers. This is a little one, 4 racks worth, and it has a whole bunch of servers, sometimes water cooled, sometimes air cooled, and you rack them up and you create multiple racks of them. It's actually a Quadrix based system. You have network switches in each rack that connect together the systems in each rack. And then you have a big switch here, which is the switch that connects together the individual high performance switches in each rack. The system always has some management nodes, and it will have some storage as shown here. So in terms of building a computer, I would say the compute nodes themselves, CPUs and accelerators, probably account for 60% of the cost of the system. The running costs are not included. The interconnect probably costs about 15%, and the storage maybe another 15%, and then a small amount for the bits. So unless you buy an interconnect, it can't run as a supercomputer. So you've got to spend some of your budget on an interconnect. Unless you buy some storage, you've got nowhere to put your results or nowhere to put your data. So if you're doing weather modeling, you can imagine that you're reading thousands of gigabytes of data every time you do a computer run and writing those results out for data points all over the Earth's surface for every time step in your simulation. And as I hinted at before, the running costs over 3 years are probably similar to the purchase cost. So a £100 million computer will probably cost you about £30 million a year just in electricity, just to run it. And that's both power and cooling. So I'm just looking at the notes. So I moved from Manchester University to work for Quadrix, who are a company based in Bristol. Quadrix produced an interconnect. In fact, Quadrix were a company that came out of Mako. Mako came out of INMOS, and INMOS was a UK government initiative to build a computing industry in the UK. That goes back to from the 1980s onwards. So an interconnect consists of a bunch of computer cards that go in the servers. That's one that's got a PCI card on it. And then they connect up to your switches, and you build your switch topology. You've got to build a topology of all your switches. So every blue circle here is a switch, a network switch, and you have your data coming into your first switch, and then that connects to other switches. And you've got to have as many switches in your second level as you have in your first, because you don't want to have any hotspots, any network congestion. So if traffic from the first node goes up the first wire up to the first blue circle, and maybe down that wire to a computer node, which are the pink boxes, that's connected to the fourth switch. Well, if this computer sends data to this one over here, it's got to go via a different route. So although it can go up its own wire here, it can't go up that line because that's already fully in use by what I've just said for the first pair of nodes. So it has to go up a different wire, and maybe it comes up this wire over here, and then comes down that link and goes to the node it's got to go to. So when you build these networks, it's not just a case of connecting a single wire or a couple of wires between each switch. You have to design a system where you have as many links in each level of the hierarchy. And there are different topologies. There's been hypercubes in the past, 3D torus. There's one that's got the amusing name of a flattened butterfly, which is a bit cruel, really. The current name of favour of that is actually the dragonfly network, because when you draw it, it looks a bit like a dragonfly's wings. But that's what we did at Quadrix. So when I worked at Quadrix, we didn't design the whole supercomputer. We made the interconnect component, and then we went in somebody else's computer to build a big system. After I worked at Quadrix, I worked at Clearspeed. This is a Clearspeed card. Again, you can see it looks a little bit like the card and the other one. They're both plug-in cards. We weren't making the host CPU, the Intel CPU type thing. We were making, for those two companies, components that you built a supercomputer out of. This was Clearspeed, also a Bristol-based company, also a derivative of Inmos and ultimately, Inmos and Viamaker. This card was originally designed for GPU use for graphics and then got converted into one for high performance computing. And what's of note of this system is the world's first computer with an accelerator in the top 500 was one of these. It was built in Japan. So although the company is long gone, it had a couple of claims to fame, one of which it had the first GPU accelerated computer in the top 500 list in its day. The other interesting movie note, and I've heard a talk last week, there's a professor at Bristol University called Simon McIntosh Smith, and he gave a talk last week. One of the points he made was that at a supercomputing show, we demonstrated a system that had I think 10 servers. There was 12 of these in each, 120 of these cards, that made that computer would have been powerful enough to be in the top 500 list, and it was on the show floor. It was a computer powerful enough to be in the top 500, yet it was in a single rack in the middle of a room of people wandering around and taking photographs and so on. And that's because I showed those pictures of these massive supercomputers that take up huge amounts of space like a basketball court. When you have a GPU accelerator, you get a lot of computing power in a small space. And that's why almost all new supercomputers now have GPUs in them to accelerate them. And NVIDIA is the market leader at the moment. So here's what I made earlier, or rather it was just before I joined the company. This is ASCII Q. It was number 2 in the world at the time. Every one of those racks contains I think it contains 6 servers in each, and each one has 4 sockets of CPUs in them. That picture is only 2/3 of the system. The final third, it was never built because of a problem with cosmic rays, which I'll come to shortly. So although the system was installed by HP, it was actually Quadrix was the glue layer that glued them all together, the network cards like I showed previously. And so the computer was delivered in 2003 by HP, and I work for them. But really, HP shouldn't get the credit, because the year before, HP had a merger. At the time, it was the biggest merger in the IT industry, and I think there's only been one bigger since. I think it was the Sun, when Sun and Oracle merged. It was only once been bigger than that. But for $25 billion, and that was a lot of money in those days. It's a lot of money now. HP merged with Compaq. So when the system was designed, it was actually a Compaq supercomputer. And HP got the credit, but it was only because it was installed 6 months after the merger, but it was designed and the components were built while it was still part of Compaq. So the Compaq Alpha server really should take the claim here, because HP just bought the company that produced it. And actually Compaq itself shouldn't take the claim, because Compaq a few years before that acquired Digital. So the chips in these are DEC Alpha chips, made by Digital, the same chips used in the Cray T3 that I showed a picture of at the beginning. So really those companies, as heritage of those companies, acquired each other. And HP is now HP Enterprise, because the printer division has been sold off. So really all these names have accumulated into HP. Actually, there's 2 other companies of note which have also merged into HP, which is both Cray and SGI. So Cray and SGI, although the brand names might still be around, they're both parts of HP Enterprise. And I thought I'd better mention what happened with the cosmic rays. The computer chips were designed without ECC memory. They were vulnerable to bit corruption. And they built this computer at Los Alamos. Los Alamos is high desert in the USA. It's over 1,000 meters above sea level, where there's a lot more cosmic ray activity. And this computer suffered from day one of switching it on. It suffered from random crashes. Those random crashes were caused by cosmic rays. And it took them 6 months to work out what the crashes were causing them, what was causing them, because it wasn't nearby nuclear weapons facilities or anything like that. It was cosmic rays crossing the universe that were coming through the system and causing bit errors in one of the caches. So actually this system, although it cost many millions of dollars, didn't really work, unfortunately. The best use case of it was the cosmic ray detector. So really I'm coming towards the end of what I was going to talk about. So I thought I'd just finish with where we're going in the future. So we now are getting into the exascale era, and what could be the first computer that is exascale is called Aurora. Will be at Argonne National Labs in the USA. It's badged Cray there because Cray is still a brand within HPE. But really Cray is part of now part of HPE, and you can see the Cray logo is actually an image of the original Cray 1 with its seating area in it. It is likely, though, that China will overtake the USA in supercomputing, because they have at least 3 projects to build computers that will be at the top of the top 500 list. And so the expectation is, although there is this USA system and a couple of others, that dominance of the list of supercomputing may be done by China, because China, whereas other countries have to design computers and have a reason to build them, China can just build computers just because it can, because it's a government-controlled economy, so it can throw as much resource as it likes. And the limitations to building a supercomputer are mostly about cooling, power, and the cost of powering them. So if you can afford to power your computer, you can build it as big as you like, and you've got a way of cooling it. And the only other thing of the story is, you might think of, where does quantum computing live in the story? Certainly quantum computing is part of the future, but quantum computing isn't high performance computing. It isn't HPC. There are no floating point numbers as such in quantum computing. Quantum computing solves a different class of problem to these. So although people say, well, where does quantum computing fit into supercomputing? As we see it from today, quantum computing isn't really part of the story. It's a different sort of computing. A quantum computer may beat one of these computers in solving a cryptographic function, basically into cracking passwords. A quantum computer could be a lot better at cracking passwords than a traditional computer like these. And so it can compete with HPC systems in some areas, but really quantum computing is a different branch. used for solving different classes of problems. I think I should stop there. So although I haven't talked for quite an hour, I think I'll stop there and hand over to any questions.
Brilliant, Daniel. Thank you very much. Very, very good. Very, very interesting presentation, Daniel. Really, really good. Really, really interesting. We have a couple of questions here. I can see you got the first one. So we have Stuart.
About the Cray 1 versus the Cray 2. That's the only one I think I can see at the moment.
Yeah, we have a couple. So that's the first one, Cray 1, not a Cray 2. So we have Stuart. We have, so I'm going to read some of them. So George is mentioned, just to share something, yesterday at a IEEE meeting that was described a project they called, it was Beyond the Supercomputer, Colossal. So it's just sharing it here.
Colossal? I'm not sure that's something I'm aware of. And again, I'm struggling slightly to be able to see. I've got like a one line of text where I can see one line of text at a time.
Can you scroll down? When you scroll down, there are the others, and then you can click on the others. I don't know if you can see it, Daniel, sorry.
I think it's constrained because I don't get many lines for the question. It's a small box.
Oh, I see. I'm posting it to you in the chat then.
But if you post it into the chat, I'll see that because that comes out large on my screen.
Yeah. So that's the first one, as I mentioned. So George is sharing that with us. So I'm just putting it here. Don't know if you want to comment on it, Daniel.
Oh, you got the link there to Colosseum.
Yes.
I can follow that link. It's not on my radar as part of the HPC world. In fact, what I'll do is I'll stop sharing. That'd probably be easier. Seen too many other things. How do I stop sharing? Right, so that's back on the title slide.
That's fine.
Okay, it's not a system I'm aware of. I'm just looking at it now. But then perhaps it's not particularly large, that system. So to be honest, I can't comment on that one because I don't actually know anything about that one.
I have posted the other questions as well, Daniel. You should be able to see in your chat area.
Let me move that across onto this window.
So I have a couple of other questions, and anyone in the attendee list, if you have other questions, feel free to drop. Then I put in the chat all the questions. I don't know if you can see them now.
So I can see the IEEE one about that one, and then so yes, through the questions. So the one I can see there is about asked by Chris is what Linux distribution is the most popular. I would say that the Red Hat is the most popular, but because Red Hat charge a license fee, then systems are more likely to be a Red Hat copy. So they will tend to be, was CentOS until Red Hat got a bit messy with CentOS, the scientific Linux, which is also a variant of CentOS. So most common is Red Hat and Red Hat derivatives. In European countries, you'll find SUSE. So the second most popular one is SUSE and SUSE-like systems. So SUSE Linux is particularly popular in Germany. And I know at Cray likes SUSE better and HPE like Red Hat better. So the systems that I work with, I would say in the same system, some components are Red Hat and some are SUSE. So there's a good question actually from George about HPC on the cloud. It's a big topic and there's lots of debate about it and has been for years. So the starting point is that for a cloud work, the economics of the cloud work best where you want to scale it up or down on demand, and works best where you don't need the system all the time. And that's where it's cheaper not to own your own kit, but to use somebody else's. But with HPC, if you're doing climate modeling or if you're doing research, drug discovery, and so on. When you buy a supercomputer, you run it all the time. You queue jobs up to it all the time. It doesn't have peaks during the day and quiet at the nights and the weekends. It's busy all the time. So the on-demand advantage of the cloud diminishes because you're not because you're going to use it all the time. And therefore, remember that a cloud, there's nothing magic about the cloud. The cloud is just somebody else's computer. So when you're running in the cloud, then all you're doing is running on somebody else's computer, and it's always going to be cheaper really to run your own computer without the overheads of running on somebody else's. But there's a lot more to it than that. So if you need to do cloud bursting, that's the role for the cloud. So if you have your own smaller supercomputer, and sometimes you need more capacity, then it's worth bursting to the cloud and running some jobs on the cloud, but you keep your main bit in-house. And also there's another challenge with the cloud is the cloud likes virtual machines. The cloud is based on hyperconverged virtual machines, not about performance. So you always take a performance hit running in the cloud. And when you build these supercomputers, you want the maximum performance you can for a given set of hardware without the overhead of virtualization, and also without the constraints of cloud systems where you don't necessarily get a high performance network. You don't get InfiniBand or similar high performance networks. So there are a lot of challenges there. But the biggest problem with the cloud is data. That the cost of putting data into the cloud is cheap. The cost of keeping data in the cloud is moderate price, competitive, not cheap, but competitive. The cost of getting data out of the cloud is massively expensive. So if you run your computer simulations in the cloud, the cost of downloading that data to process it locally is massive, something like 30 times the cost. So if you're in the cloud and can stay in the cloud, you might be okay. But if you've got to move your data around, it's massively expensive. And that's where the cloud companies make their money, from the data transfer costs. Having said all that, there is a slightly interesting case where the Met Office have take 5 years to design their next computer system. They've just designed and purchased their latest one. It's going to be a HP Cray computer, but it's going to be not in the Met Office's data center. It's going to be in the cloud. In fact, effectively, Microsoft will run the contract. Microsoft are building a cloud facility just for running a Met Office supercomputer. So it's unusual. It's not the public cloud, it's a private cloud being run by Microsoft with a Cray supercomputer in it. But that's what the new Met Office system will be. And the reason for that is one other reason why HPC the cloud has a role is that if you're faced with the massive cost of building a new data center, then maybe the cloud's an option for you. The Met Office's problem was they didn't have the ability to build a new data center in Exeter. There's economics, and also if you're the Met Office, you need to replace your supercomputer with the new one and have the two running alongside each other for a few months while you transfer over and get confidence in the new one. Well, the problem with the Met Office or similar organizations, they would need to have twice the data center capacity for a few months while they run the old and the new at the same time. And that's the other reason why it was worth the Met Office outsourcing their computer somewhere else, because they couldn't have the electricity or the space to have two supercomputers or twice the capacity at the same time. And also there's a final one. I'm a cynic. The cynical answer to that question, why the Met Office did that, is because when you're running in the cloud, you're running on somebody else's electricity. And therefore, if you're trying to be green, if your university or your Met Office is trying to look green to the public, the best way you can be green is to not have a computer on your own site, but use it on somebody else. Let somebody else run the computer for you. And therefore you appear much more green as a company or as an organization if you use cloud resources, because you can pretend that your carbon footprint's zero because it's somebody else's computer. That's a cynical answer to that. That it's if you run somebody else's computer, you can claim to be more green because it's not on your own premises. But people have been talking about HPC in the cloud for a long time, and there has been very limited uptake. So for the various reasons I've said about the virtualization, lack of interconnect, cost of moving data, and so on, HPC in the cloud still hasn't taken off. It's still a lot more expensive to do it in the cloud than do it on premise. And maybe things are narrowing a bit, but it's still the case. Running on the cloud, and you mentioned three of the top ones there, Azure, Amazon, and IBM. They all have cloud-based services. They all differ slightly in terms of what cloud service they provide. And so what there is, and I mentioned private cloud is a way forward, where Amazon, for example, rather than on Amazon's data centers, Amazon run your data center for you. So they use Amazon's hardware and Amazon software, but they put it in your data center. So they'll build a cloud on premises for you. So when you talk about cloud, you used to think about public cloud, about running on your premises or running it on Amazon, AWS. But really there's a middle ground now where Amazon will run their stuff in your own data center and so on. So I hope that answered the question. But the debate goes on about HPC in the cloud. It's still it hasn't taken off. Yes, sorry, Exa is 10 to the 18. Thank you, somebody's correcting my units. I thought Exa was 10 to 15. I have to work it out on a pencil and paper. Point is 10 to the 15, that's right, Exa is 10 to the 18. So yeah, I stand corrected there. Versus risk. It would be better if it was risk. In fact, in terms of architecture, I could have done a whole talk on computer architectures. CISC is the most general purpose. But where we stand today is we're augmenting CISC with GPUs, with coprocessors. And coprocessors have a lot of the economies of scale that you don't get in CISC. You know, the superscalers and lots of architectural reasons. And indeed, GPUs are largely SIMD. So when you talk about CISC versus RISC, I should also argue that CISC doesn't really exist anymore. Although there was a distinction 20 years ago between CISC and RISC architectures, I would say that there's not really a big distinction between the two anymore. We can argue about that over a beer sometime, but CISC has got many RISC features now. And RISC, likewise the other ones, there isn't really a big distinction, RISC being a reduced instruction set compared to a complex instruction set. But what is interesting is even though we run on CISC architectures, they have SIMD in them, simultaneous single instruction, multiple data. So your AVX instructions on an Intel CPU and similar, you issue one floating point multiplication command and it multiplies together 8 numbers for you, 8 numbers with 8 other numbers. And that width of that SIMD is only getting wider. And that's where you get your computing power, your compute efficiency from, because you're not decoding one instruction that does one multiplication. You're decoding one instruction that does 8, 16, 32, 128 multiplications and adds at the same time. And so that SIMD architecture, which we could talk at length about, isn't really CISC, I would argue. What is interesting, though, we talk about architectures, is the rise of ARM. So ARM as a processor has spent most of the last decade in mobile devices and your Raspberry Pis and so on. So ARM is very good at being power efficient. And so what we start to see now is an explosion of, in the next few years, ARM-based supercomputers because of that power efficiency. Because if you take the technology that's been developed the last 10 years that's been in your mobile phone and the ways of reducing energy consumption, turning off any part of the chip that is not in use, turning it off, that lets you build a very power efficient computer. And similarly, you talk about I mentioned about the M1 from Apple. I have a work MacBook. Sorry, I have a work HP laptop, and I have my own personal MacBook. When I go away and take my ordinary Windows laptop, I take my charger with me. because I can only run a few hours on my Intel-based laptop before it runs out of power. When I go away for the day with my MacBook, I don't bother with the charger. I can work 8 hours on my MacBook and still have battery left over. This is not an advert for Apple. It's just the CPU in Apple computers, the M1 chip they use now, is very power efficient. Therefore, those things like that are why ARM or M1 or similar chips will be are being looked at very seriously for high-end supercomputing because of their power efficiency. And the power efficiency means two things. It means it costs you less than $3 million a year to run it. It also means that the more power a computer uses, the less closely you can put the components together, so the more space it takes. And if your components use less power, then you can put them closer together. We can run more cores on the same die. So the limiting factor of Intel processors is power consumption. AMD are better at that, which is why AMD have more cores on a processor than Intel do, because they're better at managing the power efficiency. Okay, so the questions coming in thick and fast. Euro HPC, I would like to think so. So the Euro HPC, the big one at the moment, is a system in Finland. And that system's called, it's the Finnish word for snow. I forgot what it is now, somebody remind me. That's just been installed, that's just coming online. There has always been a European desire to have its own supercomputing industry. And it's not just against Chinese domination, it's also against American domination. So I work for HP, which is an American company. I used to work for IBM, also an American company. But I did want before then work for Bull, which is a European company. And there is a desire to not use foreign, to support our own computer industry. And if you're in intelligence communities, you really don't want to use Chinese equipment because you don't trust it. You should be able to trust the Americans, but it'd be better if we could use our own locally produced systems as much as possible. And so I think Euro HPC is a great idea, but I think part of the story isn't just compete against the Chinese, it's about competing against the Americans as well. And so we have a critical mass of not just hardware, but also development. And so it's interesting that Cray's R&D development for its interconnect is based in Bristol in the UK, not in the USA or in India. So yes, I think Euro HPC products are great. I think it has more of an effect of where we stand compared to the USA, whereas it's where we stand against China. In terms of programming, of course, it's massively parallel. So if a computer's got 1 million CPU cores, you're writing a computer program that has a million simultaneous executing processes at the same time. And so each of those million processes has to exchange data with the other 999,999 processors. You tend to use two-level parallelism now, where you tend to have a OpenMP parallelism within a CPU, certainly within a die, and then a message passing MPI between the sockets. But the boundary of what counts as OpenMP and what's MPI is, it depends on what you want to do. And for some applications, you have one MPI process per CPU core. So you run a program where you launch the program and you launch 1 million copies of the program at the same time. And again, the first top 500 list, for the first few years, maybe the first 8 years, there were computers at the top that were single CPU computers, vector computers, so they could do vector instructions, but there were single CPU instructions. That hasn't been the case for 25 years. So where we have been for the last 25 years is the only way you can use these supercomputers is by writing parallel programs. And the most dominant way of doing it is MPI, the message passing interface, where at a certain point in your program, you call a subroutine, a function which will write data to another system, and then a corresponding function on the other side will read it back. And just in passing, by the way, Fortran is still the dominant language in supercomputing. followed by C. I guess it maybe level Fortran and C now, but Fortran is still the language of choice for most scientific codes. HPC, why did I get into high performance computing? I think because it's big and clever. I think I always did computers stuff at school. In fact, in my early days, I remember using a teletype. My father was a teacher at school, and back in the 70s. And when he went into school as a science teacher at the weekend, sometimes to prepare things, that I would go in as well, and he'd park me in front of a teletype, and I would place lunar lander games on a teletype. No display screen. It just had paper tape and punch cards. So that's what got me into computing probably in the first day. But I think I decided to do engineering as a degree course, but I just got into the large scale simulations is exciting. So I got into HPC because it let me do things that I was doing in engineering, but do it at very high end. And also HPC is doing things that have never been done before. It's always striving to do something twice as fast as what's ever been done before. Whereas other areas of computers are more about flexibility. So a lot of computer paradigms now are about Kubernetes and things. It's not about doing it faster. It's doing it by doing it with more ease, more automation, and more easy to run your jobs in different places. Good question about the most efficient. There is a second top 500 list, which is called the Green 500. And that takes the computers in the top 500 and ranks them according to power efficiency. So it's the same computers, but ranked according to power efficiency rather than peak performance. And they measure it in teraflops per watt or watts per teraflop. So how many compute cycles you can do for a given watt of power. And so yes, the top 500 list website, which you can look up, also includes figures for what's called the Green 500, which is energy efficiency. And you'll see that they're dominated by GPU-enabled computers. So even the computers that are not at the top of the list are dominated by systems that have GPUs, because they're much more power efficient per floating point operation. Yes, so the question that came in at 2031, I did mention it in the talk. I was talking about the Met Office. The Met Office are using Microsoft Cloud, so I'm involved with that project myself, because the system that's going in is a Cray system, and HP and Cray are the same company now. But because the Met Office didn't have the ability to build a new data center in Exeter, and on the ability to power it as well, power and cooling for it, that contract, although multiple vendors bid for the contract, the one that won was HP Cray. For the supercomputer, HP and Cray can't build a cloud. HP are not a cloud company as such, as in they don't have a large data centers, not like Amazon. So that bid is hosted by Microsoft. Microsoft have no systems in the top 500 at all. So this will be the first Microsoft system. Microsoft will get the credit for being in the top 500 for the Met Office system. And it's actually not one system for the Met Office. The Met Office always have at least 2 computers, because the Met Office have to get the weather forecast out every 6 hours. So they will never be able to shut down. If they only had one system that was a single system, they could never shut it down for maintenance, because they have to produce weather forecasts for the military, for airports and so on every few hours. So they can never shut the whole system down. So they have to have at least 2. In actual fact, the Met Office actually got 4 systems, 2 halves, with the larger and the smaller part of each. But yes, the Met Office project is interesting in that they have gone to a cloud-based solution, but it's a fully hosted cloud, and it's hosted by a company you wouldn't expect, Microsoft Azure, who currently have no systems in the top 100 at all. So a question from Chris. how efficient are HPC at crypto mining? So I'm not sure if we talk about the same thing, whether you're talking about crypto mining or talking about crypto attacks. So if you're talking about mining for Bitcoin, then they're reasonably good at it, particularly the GPUs are. There have been a few cases where, in fact, there's an embarrassing one for, I think it was Edinburgh University, or was it Durham? Their system got hacked for people who wanted to use it for cryptocurrency mining. I think the cryptocurrency one has less need of floating point maths, but yes, they are quite good at it. I would say if you're mining cryptocurrencies, you need a lot of computing resource, but they don't need to talk to each other. Each process is independent of all the others. So you can do crypto mining using arrays of computers, at people's homes, say, if you can attack their computers there, or otherwise. You don't need, there are two components of a supercomputer system you don't need for crypto mining. You don't need high performance storage. So you don't need to store millions and billions of petabytes of data. Sorry, you don't have to store petabytes of data, or millions and millions of bytes. You also don't need an interconnect. And I said that for a supercomputer, at least 30% of that system's cost is in the interconnect and the storage. And for crypto mining, you need neither. So if you're designing a system for cryptocurrency mining, you wouldn't bother with those components. You just go for the compute part. In terms of the other part of the question, if we were talking about malware, then that's more of an attack against, well, there's two sorts of malware. There's the crypto encryption of files. So if you're worried about that, what you have to have is a file system that protects you against ransomware. And the way of protecting that mostly is about taking snapshots. And what I do as my day job is mostly about file systems. And that includes how you protect against malware by taking snapshots of your data every few hours, so you can always wind back to a state of your data before you've got the crypto attack. And also there's a related topic of using AI. Now big firms have AI solutions that watch their file systems and they will spot unusual activity. So if a bank system starts seeing unusual activity in its file systems, it will suspect there's a crypto attack, because the right file read and write access for a crypto attack is very different to normal everyday access to data, because it reads the file, encrypts it, and then reads the next file and encrypts it, which is very different file behavior to normal. So AI is very good at spotting those. The other malware of interest is the ability to read what's happening in CPUs, as in, can you read the memory of another person's process? And the people that worry about that are the people in the intelligence communities and AWE, people like that in the defense industries. And they largely protect themselves by having their computers not connected to any network and only running jobs of a certain classification on that computer, never a higher classification or lower one. Because if you run on the same supercomputer a higher and lower classified work, then effectively each taint each other. So that potentially the lower classification work might be able to read data at a higher security classification. So they tend to keep them separate. So the last question in the list I've got here is MTBF. And this is where you've got to talk about the difference between NTBF and MTBI and similar things, MTTR. There's a whole world of different things in terms of failures. So what you do in a supercomputing system is you actually accept the fact that you will get failures. If you build a system with 10,000 hard drives, which is typical, you'll get at least one failure a day. So you build a file system which it will cope with the fact that every week you'll have about 7 failures of hard drives, because you build yourselves with software RAID across your drives, so you can cope with drive failures. In terms of failure of a computer node, yes, they happen as well. You try to design them away, but it'll still happen. So if you're building a computer of 1,000 10,000 compute nodes, you will get failures. And the way you protect yourself against that is checkpointing. So your computer job that runs for 8 hours will perhaps every 20 minutes write out its state to disk or flash drive. And so if you get a node failure, you restart your job from the last known state. So you read your data back from your disks or flash drives that you've taken every 20 minutes, the restarts. And so a typical long running job may well restart multiple times because of a node failure, has to restart and load its data from the last known snapshot taken of that run. In fact, there's more to that I can talk about as well, but that's one reason why supercomputers need fast parallel file systems, not just to write results out after they've been running for 8 hours, but to write out intermediate results every few minutes. And that's to protect themselves against hardware components, because the mean time to failure of one server might be 3 years, but the mean time to failure of 1,000 servers comes down to the order of 1 or 2 failures a day at such large scale. You also mentioned about bits, and bit corruption is also important. You need to protect yourself against bit corruption. So you need to protect yourself against bit rot. So a bit, if you transfer over your network billions of bits a second, then even if you have a 32-bit checksum, you will get bit errors which won't be detected because you'll get a matching corruption in the checksum as well. And so you won't spot the mistakes. That's why you need higher level checksums and forward error correcting, FEC and things like that. So you can correct yourself live from errors. Bit rot is a potential serious problem, and certainly failures. All supercomputers will have failures of components almost every day, but you try to build a system where you're resilient against those because you can restart. Right, so a question from Daryl. Are the materials used for the manufacture of HPC, the CPUs and interconnects, changing over evolution? What happens at the end of life? I'm not sure I fully understand that question. If I go back to one of my graphs, what you find is that when a supercomputer is installed, it has a lifetime of probably not much more than 3 years. It tends to have, I would say, typically it has a lifetime of 6 years. 3 years as being a production system that is, good, and maybe a further 3 years as a legacy system that still works, but obviously has been outdated because there's better, faster CPUs and faster interconnects that have come out since. And so what is not unusual is a supercomputer gets put in for 6 years, and after 3 years it gets upgraded. So for example, the system I worked on at AWE, where they knew there was a next generation of Intel processors coming, so they built the system with the processors that were available at the time, but they knew that the budget in the contract was that 2.5 years later, when the next generation of Intel CPUs came out, they replaced all the CPUs in the system with the latest CPUs. So people do design supercomputer systems knowing they'll upgrade halfway through by putting more memory in, by upgrading the CPUs and so on. I'm not sure if that answered the question. You could also talk about the technologies, and really you do get there's an idea that when computers are not used anymore, they might get sent for other uses. But I'm not sure there's much of that actually happens. A lot of computers, when they're end of life, they really just get recycled for parts. They go for recycling to get the metals back and so on. The computers themselves, and you see by the way the top 500 list has moved from each era only lasts so many years before systems are 1,000 times faster than the era before. And so what that leads to is the systems do get obsolete, and there's just not a lot you can do with the old computers. And so they do get thrown away or say recycled for the metals and so on. I'm not sure if that answers your question or not. But that's all the questions I've got. I'm not sure if I missed any questions. I was scrolling through the list, but I hope I answered all of them.
Yes, Daniel, those are all the questions we got. And I think, again, a big thank you to you, Daniel, for all these amazing talk and all the questions and answers we got, both from the audience and the answers from yourself. I thoroughly enjoyed, particularly the interaction. So thank you very much for everyone who asked your question, and thank you again, Daniel, for the answers. They were incredibly informative. Thank you very much for everyone who attended, and the branch will continue to offer monthly webinars. We are preparing very, very good and interesting talks as well, and we'll be, as usual, sending everyone an invite and information about the following talks. Daniel, once again, thank you very much. I don't know if you want to say anything else before we finish the webinar.
Just that I did post that you can find me. My name's Daniel Kidger. I'm out there on LinkedIn and so on. If anyone's got any follow-up, you want to ask me any questions or connect with me, then just look me up and I'm happy to engage.
Brilliant.